We'll just stop anytime if anything is unclear. So here I give a quick example just to make sure that everyone is on the same page. If we have parking preference 1, 2, 2, 3, it means the first car prefers spot 1, second car prefers spot 2, and then as you can see, both cars will take their preferred spot. And then the third car prefers spot 2, it's already occupied by the second car. So the third car will drive forward and park in the next available spot, which is spot 3. And then the fourth car prefers spot 3, so it will drive forward to park in spot 4. So it is 1, 2, 3, 4 as a parking outcome. Right? And then for another example, 1, 3, 3, 2, as you can see, 1, 3 are both available. So the cars park here. And then this 3 is already occupied by the second car. So it will drive forward to park in spot 4. And then this 2, it will park in spot 2. Right? And then 2, 2, 2, 4 is not a parking function because the first car will park in spot 2, second car will park in spot 3, and fourth car will park in spot 4, and then the last car will have to leave the street. Okay, so simple criteria for things to be a parking function. So using the pigeonhole principle, it is not too difficult to find that it is a parking function if and only if the number of preferences less than or equal to I is greater than or equal to I. And then this needs to hold for every I equals 1 to n. And then the argument can be done inductively. For example, if you consider spot n, you can have at most 1 car that prefers a spot. Because if you have 2 cars that prefer spot n, then 1 will need to leave the street. And then you just go backwards and then go to spot 1, and then you write it in another way, you get this. And then there is another way to see this pigeonhole principle is by looking at the non-decreasing rearrangement of the preference sequences. So if we form the non-decreasing rearrangement, we will have lambda I is less than or equal to I. And then these two conditions are equivalent under switched off coordinates. And then from these, either the pigeonhole principle or non-decreasing rearrangement perspective, you see that a parking function is invariant under the action of permuting the cars. So if you permute the preferences of the cars, you will get different parking outcomes. But if something is a parking function, then permute it in any way you like, it will also be a parking function. If it's not a parking function, then permuting it in any way you like will not help you either. All right, and then, so yeah, just some late review. For parking functions, people have studied in connection with other combinatorial objects. And then Stanley connected parking functions to hyperplane arrangements, interval partitions, interval orders, and plane partitions. And then for self-organized criticality, Corey and Lawson were able to establish that G parking functions were equivalent to a billion centiles. And also Pittman Stanley studied volume polynomial polytopes. And then there are other generalizations of parking functions. For example, U parking function, G parking function. And then people studied symmetric functions, diagonal harmonics, and then other generalizations include rational parking function and parking with variable car sizes. So there are many generalizations. So the setting I told you about just now was a basic setting. And then from the probability perspective, people have also studied like adding probability layers to parking functions, and then found connections to the widths of rooted labeled trees, empirical processes, and Brownian motion. So in particular, when the number of cars equals the number of spots, you will see Airy processes, and otherwise you see Gaussian processes in the limit. And also a particular statistic for parking function is called total displacement. And then for this statistics, yeah, so you will see Gaussian, Airy, and Poisson, depending on the ratio in the limit. And also there are parking functions with defects. namely that some cars will not be able to park, and then you study like K defects, exactly K cars cannot park, and so on. So there are various perspectives people have taken for parking functions. And then today, more diachronism here study the asymptotic distribution of parking functions. And then, yeah, we also use the multi-shuffle construction to study the particular coordinates of parking functions. And then some people in the audience have also done work on parking functions. Today, we are going to look at one particular generalization of parking functions by adding a probabilistic layer to the standard model. So the idea is the following. We still have n cars enter a street with n available spots. And then now, if the spot is empty, the car will just directly park. But if the spot is occupied, the car will not automatically drive forward. It will flip a coin. And then if the coin tips heads, the car will drive forward. Otherwise, the car will drive backward. So it drives forward, try to find the next available spot to park. And drives backward, also try to find the next available spot to park. And then we will assume that P in 0, 1 is the same for every car. But like every car has this forward or backward probability. So the idea is that when a car enters the street, it does not only carry with itself a preferred spot, but also a preferred direction. And then the reason why we do the same fixed P is because it is easier to implement in data science, because like we use random bits to store the information for a car. And now if the car has a preferred direction, we just need one bit of information to store that direction. And then, yeah, I'm just explaining this here. And the classical situation corresponds to P.
One comment, I guess in other applications it's okay. But for this particular application, backward, you knew if you know if there's spots available or not. Yes.
You don't know.
You drive in that way, yes?
Yeah.
So that you saw it in the past. I mean, just for this particular application.
No, it's like the car. So in like hashing, it's like you try to put items in a hash table, and then you directly put it in that item. You just drop it there without
so
actually
you don't see it. Okay.
Yeah, yes.
The driver has no memory.
Okay. Okay, that's fine.
Yeah, that's right.
Or maybe it's yeah. I was thinking maybe the car after you already parked, but then you cannot backward. But anyway, okay, it's irrelevant.
No, it's actually very relevant. Yeah, so, and then the classical situation corresponds to P equals 1. So every car will just drive forward. Okay. And then let's see. So now adding a probabilistic layer, again, like a picture illustration, just to make sure. So we see that if we have preference vector 1 to 2, okay, first car parks in 1, second car parks in 2, then the third car will need to choose this direction in order to make it a parking function. So this direction will not. Now you see like every preference sequence will now have some probability of becoming a parking function. And the probability will depend on the previous, the specific sequence. So this sequence 1 to 2, the probability of making this a parking function is P. And then, so what is special about this is that now there's some nice symmetry embedded here. So one is that we now have preference symmetry. We see like, again, like the cars, you're just thinking they directly will parachute it down to that spot. And then if the cars drive forward with probability P and backward with 1 minus P, it's like cars entering from the other street, the other way. And then it's forward with probability 1 minus P and backwards is probability P. So that's a preference symmetry, which now appears. with this layer, but then also lack of permutation symmetry. Originally, we know that if it's a parking function, then permuting it in any way, it will be a parking function. But now, if it's like we know every sequence has some probability of becoming a parking function, and then permuting it will give you a different probability. So now we have lack of permutation symmetry here. So for the previous example, you can already see that. Yeah. We should also mention that here, pi in PFA is just a shorthand for the situation that n cars with preference vector pi park. So every preference sequence will be able to park just with different probabilities. So we interpret this as saying, okay, what is the probability of such an event happens? Right. And then the main theorem one in our paper is this result. So it turns out that independent of P, the total probability of something being a parking function is still given by this. So for P equals 1, we see earlier that the total number of parking functions is n plus 1 to the power n minus 1. So there are n to the n possible preference sequences. So total probability is that. And then for different P, actually, it's the same probability. Okay? So it's kind of magical. And then here I just listed for n equals 3. These are all the different probability for the 27 preference sequences being a parking function. And when we add them up, it's exactly equal to this formula. So if you add up all the numbers here, you will get 4 to the square, which is 16. So as you can see, like, for example, maybe this one, 2 to 1. Okay. So in the classical situation, when the second car prefers spot 2, it will just drive forward to spot 3. And then the third car will park in spot 1. But now there are two different situations. The second car could drive forward with probability P, and now the third car will directly park at spot 1. Or it could be the second car actually drives backward with probability 1 minus P. So it will park in spot 1. And now when the third car enters, it prefers spot 1, but it's already taken by the second car. Now it will have to drive forward with probability P. That's why we will have this. So there are more situations you need to consider in order to get such a formula. All right. And then here I will also give an outline of proof. So the outline of proof is the following. First, we will actually put all the cars in a circle with spots n plus 1. And then we will soon see that if it's a parking function, if and only if the last spot is left empty. Right, because last spot is empty means all the previous n spots are taken in some way. And then we can use symmetry of the circle. Let Fai denote the expected number of preference vectors which have leading preference A and leaving spot I vacant. And then a nice thing is that there is a permutation symmetry. So Fai will be Fbj. So leading preference A, spot I, empty, is the same as leading preference B, spot J, empty, if B minus A is equal to J minus I mod n plus 1. So you just think you permute all the sequences along the circle. And then just for illustration, we can write down such a matrix. So this is a matrix. Here, the row is F11, F12, and then this is 1, 2, and this, okay? But then using that permutation along the circle, we see that F12 here is the same, okay? And now F21 is the same as F1 n plus 1, right? By following that symmetry. And then F22 is the same as F11. So it's a horizontal shift starting from the second row. And then it's always a shift. But then all these numbers are the same. And then you can see that the row sum will be the same as the column sum. Right? So the row sum and the column sum is always the sum F1 and then to the different superscript. So, and then we use some total probability and then doing a little bit more trick, we can get the result. Okay, so after this, we were like, okay, so if P is the same, like for different P, the total probability the same, then P itself should have some influence on the parking result as well. And then we were like, okay, so what is the difference? There are many differences for different P. So in this talk, I'm just going to talk about like one or two of them. And then later I will talk about more open questions for different P, right? So I'm going to show some simulation plots, and then you will see like 5 plots, upper left, upper right, and so on. So these are the simulation plots. So they are generated over 100,000 uniformly randomly chosen sample of parking functions. And then this is for P equals 0, P equals 1, P equals 0.5, 0.25, 0.75. And these are the distributions for the last car. As you can see, there is symmetry here. P equals 0 and P equals 1. They are symmetric as expected. And 0.25 is symmetric with 0.75. So, and then for P equals 0, it means that so all the cars will try to drive backward. So that's why cars with later preferences are have more probability. But like with the thing I wanted to emphasize about these simulation plots is that the middle plot, when P equals 0.5, you see much faster convergence to uniform distribution, right? So it looks quite uniform, while the others do not look that uniform yet. Yeah. So actually, all of them will converge to the uniform distribution. The limit is just a much faster rate of convergence when P equals 0.5. And then intuitively, I guess that's also kind of makes sense because P equals 0.5 means forward, backward, equally likely. So it's kind of more uniform in some sense. And then we're actually going to show.
Sorry, I get lost here. What's the x-axis, the horizontal one? What does that mean?
The horizontal axis are the preference of the last car.
Oh,
So this is a distribution of the last car. So the last car could prefer, well, so the last car could prefer, yeah, so it's, we have size 100, means there are like 100 spots, 100 cars. And then this is for the last car. So last car could prefer any spot in between 1 and 100. And then this tells you the relative probability. Yeah. Okay. So, and then this is a theorem. Okay. It says that the probability of pi n equals j, given that it's a parking function. So conditioning on the preference sequence is a parking function. We wanted to compute the probability the last car prefers spot j, and there is actually an explicit formula. Okay. And from the formula, we also notice preference symmetry from before. So pi n equals j, and then under this protocol with forward probability p is the same as preference equals n plus 1 minus j under the protocol with parameter 1 minus p. This follows from the preference symmetry. But there is one other thing that does not directly follow, that is concavity. So the conditional distribution of pi n for generic p is actually a convex combination of the cases p equals 0 and p equals 1. And then we can write down the exact convex combination. And the convex combination later will play quite an important role in the rate of convergence.
Sorry, again, your pi in PFN.
Yes.
How is that different from pi in bracket n to the n here? Because we're assuming under protocol P.
Yeah,
it's
yeah.
possible.
So pi in PFN means
Okay.
it's a probabilistic model and
Yeah.
then trifle, and then it means that the car will be able to park with certain probability.
The non-zero probability for
Right.
for this particular P. Okay.
Yeah, yeah, yeah.
And so for generic P is
So
most
for
preference
generic
vectors?
P, we know probability pi in PFN is n plus 1 to the n minus 1
Yeah.
or n to the n. So it's kind of like normalized by that. All right, so I will also give an outline proof. So I will present outline of proof to every result here, but maybe they're really just outlines. So actually for this one, it's not too difficult. The idea is that when the nth car enters, you know that 1 through n minus 1 cars have already parked, right? And then it leaves open an empty spot k. So now for the last car, it could either directly prefer k, then it will keep directly park, or it could prefer a spot before k, then it will need to have probability p, so that it will drive forward to park. And then it could prefer a bigger spot than k, and it will drive backward to park. And then you can write down a recurrence relation. And then, yeah, this is what I said here. And then derivation of the explicit formula utilizes Abel's binomial theorem. So we will present Abel's binomial theorem. But before that, let me mention that, so all of these can be generalized. So you can consider, for example, the last 2 cars or last many cars. And then instead of looking at Abel's binomial theorem, it could be Abel's multinomial theorem. And then instead of doing something for the shuffle, you will do a multi-shuffle. So there are generalizations for all of them. And then we also don't necessarily need to look at n cars and spots. It could be m cars and spots and so on. So now, so let me first talk about what is a shuffle thing. And then I will talk about Abel's binomial theorem. So again, like this is a basic version, can be generalized further. So the shuffle idea says the following. Pi 1 through pi n minus 1, namely the preferences of the first n minus 1 cars. It's a shuffle of 2 smaller parking functions. One is k minus 1, the other is in n minus k. So the idea is that you're just thinking the open spot k before the last car enters breaks up the parking function into 2 components because the car cannot jump over an empty spot. So the first component is occupied by the first k minus 1 car, and the next component is occupied by the next n minus k cars. So that's why we have this shuffle idea. So for example, if we have n equals 8, k equals 4, then you know one should be a parking function of 3 things because k is 4, 4 minus 1 is 3. And the other should be a parking function of 4 things because 8 minus 4 is 4. And then I just randomly write down 2 parking functions. One is in PF3, the other is in PF4. And then it's a shuffle of this when I permute the digits in any way I like, but also for the beta thing, I add 4 to every digit. So 1 plus 4 gives me 5, 2 plus 4 gives me 6, 4 plus 4 gives me 8, and 3 plus 4 gives me 7. And then I add 4 because those are the cars after that empty spot k. So it's like previously I subtracted by k. So now I just add it back. Okay. And then this is a shuffle construction. Again, it can be generalized further. And also what is Abel's binomial theorem Abel's binomial theorem, this is the formula. As you can see, there are some special cases that can be calculated explicitly. There are recurrence formulas and so on. So using Abel's binomial theorem and its shuffle construction, so special cases here. So using those basic constructions, and then that we should be able to calculate the probability of the last card preferences. Okay. So because you see like some formulas here, they remind you of Abel's binomial theorem. Right? You have s+1 to the s-1, this part, it looks like Abel's binomial theorem as well. So it's like a binomial coefficient and something plus p, something plus x, and plus q. So for Abel's binomial theorem here, it's like x is 1, p is 1 when you have s+1 to the s-1. So using this formalism, like some asymptotics can be computed.
Is this a generating function for some common?
Yes. Yeah, so Abel's binomial theorem, like for example, xy -1 here, this, if you take one is 1, the other is, so both take 1, then it corresponds to trees. And so it's a generating function for some counting things. And then you can also take derivatives and they will correspond to expectations and so on. Okay, so once we have the conditional distribution of pi n equals j, then we can compute the expected value of pi n by following probability concepts, and then it will be equal to this. And then again, we see preference symmetry here. Expected value of pi n on the parameter p is the same as expected value of pi n. Well, sorry, adding expected value of pi n on the parameter y minus p is n+1, and then expected value of pi n pi in PFN is equal to this exactly on the parameter 0.5. And then to prove this, we will need to use some asymptotic expansions like Stirling's or Edgeworth's expansion with a continuity correction, because this will be approximated by Poisson random variables. And then it's a discrete distribution, and then with some continuity correction, or we can use incomplete gamma functions to do the asymptotics. So there are some like methods which we can use. And then this thing itself is the area statistics or displacement statistics of parking functions. And then it comes up in area processes and so on. All right, so, and this is just a simulation plot. It shows that when the forward probability is given by 0 up to 1, and then we see expected value of pi n decreases like this. It decreases linearly with respect to p using this. So now let's see. Earlier we hinted that for p equals 1/2, it converges to uniform distribution much faster than at other p-values. So then we were like, okay, why is that true? First, we will provide some intuitive arguments, and we will prove it rigorously. So intuitively, we were thinking as p decreases from 1 to 1/2, and the distribution of pi n will place less and less mass on cars with small parking preferences, right? Because when p is 1, you know if it's small parking preference, and then it's already occupied, it will just drive forward. Okay? And then p equals 1/2, it doesn't have that edge anymore in order to drive forward. And then similarly from 0 to 1/2, it will place less and less mass on cars with large parking preferences. So for p equals 1/2, it should be like about the same preference for every car, and that gives you uniform distribution. And then rigorously, it will show that actually it will speed up the rate of convergence of pi n to uniform distribution when p is equal to 1/2. Okay. And again, let's look at the simulation pictures one more time before we dive them to the proof. Okay. So here is the main theorem. It says that we let Q and P, just a shorthand for the conditional distribution for the last car. And then we can prove that the difference between Q and P and uniform distribution bounded by total variation distance. This rate of convergence is 1/√n for general P not equal to 1/2, and it's 1/n for P equals 1/2. And then the total variation distance, there are different characterizations for that. Here, I'm just going to give one of the definitions, which is 1/2 sum of all the differences. You can also use, yeah.
Just a quick question. Yeah, sorry, maybe you probably already said this, but so why are you so interested in the position of the last car?
That's a very good question. So we are interested in position of any car, actually. It's just that the last car is the easiest to analyze. So we can also analyze distribution of, say, next to last car, or for example, a covariance between these things. And then if you wanted to know like first car or second car, that's much harder to analyze because then, last car is like all the cars have already parked. So, but after this, I will talk about another global statistics. Yeah. So, this is the thing.
Yeah, actually, I have a similar question. So here you focus on this. Do you study more about the distribution of pi itself, like the variance of pi, or the expectation of pi?
Yeah. So, what do you mean? Values of?
Sorry, never mind. You just say that it's pi belongs to that. Let's say, okay, never mind.
Okay, thank you.
Never mind.
Okay. All right. So now QM pi p, if people remember, we derived it earlier, and then we mentioned that there is concavity and preference symmetry. People remember that? So for preference symmetry, if we write this down compactly using Q and P, we will have Qn1 of J plus Qn0 of n plus 1 minus J. Right? And then also concavity, we only briefly mentioned that it's a combination of P equals 0 and P equals 1. So actually there is an explicit formula here. And then we can establish a chain of inequality concerning the rate of convergence after some work. So it's this less than or equal to this and less than or equal to this. And then because Qn1 and Qn0 are the same, sort of, like using preference symmetry. And then you see that's why we need P not equal to 1/2. Because if P equals 1/2, you only know this total variation rate is bounded above by this. But for P not equal to 1/2, you know it's actually the same rate of convergence. Right? The magnitude will be the same. And then, then we also identify a clever choice of test function for this. And then apply both binomial theorem and the main theorem 3 will give us for P equals 1/2. It will give that rate after some work. All right, so next, let's also look at some related combinatorial results for parking functions. So this is a problem posed by Novelli and Dubon. And then it's OEIS, the sequence. So it turns out that if we are asking about parking functions on the circular street, and then So the first car always prefer the first spot, and then all the other cars can prefer any spot they like. And then I'm asking, okay, K unlucky cars. So unlucky car just means a car that was not able to park in its preferred spot. That means an unlucky car. Right? So then we find that for every K, we can write down all these numbers. So this means a parking function, for example, with 3 plus 1, 4 to the 3 parking preferences, and then you have 6A2 and so on. So for the first car is always lucky because the first car will always park in its preferred spot. And then, so K at most can be n minus 1. And then you can also write down the explicit generating functions. So U and Q is equal to this. And there are other generating functions, for example, this one. So now we also consider circular parking. But now it's only on N. And then the cars can park in any spot they like. And then you asked about unlucky cars. And then this will be the numbers. And then on OEIS, the sequence is listed under leaders in the labeled trees because for parking functions, lucky cars have a correspondence with leaders in a subtree.
I guess that's the question bigly in my mind,
Mhm.
asking for the distribution kind of. Think of the number of cars which can be parked.
Yeah.
Yes.
Yeah, so we have yeah, so if you consider, say, lucky cars, which are the counterparts of unlucky cars, asymptotically, they go to normal distribution. Yeah, because there's some independence. And then someone recently told me those are also connected to prime parking functions. Yeah, so there are more of this. Yeah, so there are obviously other combinatorial results, but further directions. So further directions are like here we consider one-way parking or circular parking. What about like two-dimensional parking or G parking, adding probabilistic layer or doing a multi-shuffle or other things? And also, what are the asymptotics? What are the correspondence between these models and other combinatorial models? Well, there are many questions people can ask. So this is about the content of that paper. And then if people don't have questions right now, I will talk about some newer thoughts I had after the paper is written, unless people have questions now. Yeah.
In reality, each car may have multiple preferred parking spots.
Yeah, that's a very good point. So yeah, but then do you assign like uniform probability to every spot?
You can do that.
That's very interesting. Yeah.
Has anyone?
I don't think so.
Because yeah, in real life, every day we drive to our workplace. As long as we can find a parking lot, it's fine. It's not necessary we need to park in a particular.
Yeah, I think that's very interesting. Yeah, people have considered like cars that will need, say, 2 spots in order to park, those things. But like multiple spots and uniform probability, at least as far as I know, I don't think people have looked into that. Yeah, okay. So now let me talk about some newer thoughts I had after the paper is written. First is to answer Jason's question, why are we like so obsessed with this last car? It's just because last car is easiest to analyze. But there is another thing we could potentially analyze, that is like the total displacement of the car, which I talked about earlier. So the total displacement of the car means for every car, you just consider how many more spots it needs to drive in order to park, whatever direction. So for example, if you have like 1, 2, 2, 3, and then the parking outcome is 1, 2, 3, 4. Then the total displacement would be 1 minus 1 plus 2 minus 2 plus 3 minus 2 plus 4 minus 3 is equal to 2, for example. And then when we add a probabilistic layer, the car could drive forward or backward, but you can also talk about the extra places the car needs to travel in order to park. And then it is not, well, it requires some work, but then we can show that the expected value of the total displacement, say if I write displacement of the J's car, the expected value of sum of all the displacement is also P independent. And actually the displacement is distributed similarly, independent of P. It's not just the sum is independent, but also expected value sum, displacement P and J, and then square is P independent and so on. So every moment it's the same. The distribution is the same. And then you're like, okay, now this is, I should also say that this applies not just to one-way parking, but also circular parking. So you drive forward or backward along a circle, the sum is the same, right? But then I'm also like, okay, what are the other P-dependent statistics besides last car? And there is indeed something. For example, if we consider circular parking, again, for one-way parking, it also defines similarly. And then we know every car prefers some spot, and then, but it might be pushed forward or backward, right? And then if we look at the number of cars, so say if a car prefers this spot, and this spot is already occupied, it will be pushed forward or backward like this. And then if instead of considering displacement on car, like concentrating on the different cars, we concentrate on every spot. And at every spot, we count the number of cars that are pushed away from the spot, meaning the cars that attempt to park at the spot, but had to leave because it's already occupied. Now it is not too difficult to show that sum of, I don't know, out J, now this sum is summed over all the spots, not all the cars. So you change your perspective. And sum out J is the sum as displacement of J. This is clear, I guess, right? Because eventually it's just viewing things differently. And then you're always counting the arrows, either this way or that way. So out J, the sum and this, even though the sums are the same, they are like decomposed differently. So for displacement J, it could be, I don't know, like 1, 2, 2. And then for the out J, it could be 1, 1, 1. So they are decomposed differently. And then we already know this is always P independent. However, this is P dependent. For example, if we sum out J square, then we already see P dependence. And actually the P dependence is very interesting. The P dependence will look like this. So it will always be a concave down curve. And then P equals a half will be the maximum. And then P equals 0 and P equals 1, it will be the same. So the symmetry should be clear from the construction because like it's a circle or one way it's also the same. Symmetry is clear, but then like why does it look like this? And this is true for any number of cars and any number of spots. And it's still an open question right now. So, yeah, so I feel like I know how to explain all of these, but then coming down here, I already don't know. And then there are many other open questions related to this. For example, here, like when we have a conflict, a car, the later arrived car always drives forward or backward. What if like we switch some already parked car out, and then we drive the switched out car drives forward or backward? Or it's always the earlier arrived car had to leave. run a newer.com. There are all these different algorithms and many open questions. So if people are interested, I'm very happy to chat. Yeah, I guess that's all. Thank you very much.
Is there any questions?
Yes. So you mentioned G marking function.